Backbone routers handle billions of packets per second. But here's a question that puzzled engineers for decades. How much buffer memory does a router actually need? For the longest time, everyone agreed on a simple rule of thumb, but a 2004 paper from Stanford shattered that assumption, and the key was basic statistics. The old rule said buffer size equals round-trip time times link capacity, written as B = RTT times C. For a 10 gigabit per second backbone link, that means 2.5 gigabits of memory. That's enormous, and it forced router designers to use slow, expensive off-chip DRAM chips. Where did this rule come from? A single TCP flow. TCP uses a sawtooth pattern. It slowly ramps up its sending rate until it detects a dropped packet, then it cuts its window in half, then ramps up again. Over and over. The buffer needs to be large enough to keep the link fully busy during that sudden drop. For one flow, this analysis is exact. You need B = RTT times C. But backbone routers don't carry one flow, they carry 10,000. Here's the key insight. With 10,000 flows, are they synchronized? Do they all cut their windows at the same time? No. They have different round-trip times, different start times, different paths. Their sawtooths are completely out of phase with each other. Think of 10,000 people breathing in a large room. If one person takes a deep breath, you'd notice the air pressure change. But 10,000 people breathing randomly, in and out at different times, the fluctuations cancel out. The aggregate is nearly constant. This is the central limit theorem at work. The sum of many independent random variables converges to a Gaussian distribution, and its variance grows only as the square root of n, not n itself. Mathematically, the aggregate TCP window, the sum of all flows' congestion windows, is approximately Gaussian. Each flow's window oscillates with some variance. For n independent flows, the total standard deviation grows as the square root of n. So the buffer only needs to absorb those square root of n fluctuations. The new rule becomes B = RTT times C divided by the square root of n. The square root of 10,000 is 100, so you need 100 times less buffer. The paper validated this with over 15,000 network simulations and experiments on a real Cisco GSR router. A 10 gigabit link with 10,000 flows needs only about 25 megabits of buffer instead of 2.5 gigabits. That's a 99% reduction. 25 megabits fits in fast on-chip SRAM, no more wide memory buses, no more off-chip DRAM, simpler, cheaper, faster routers with no meaningful loss in throughput. By applying the central limit theorem to TCP traffic, this paper showed that backbone router buffers can be 100 times smaller than everyone assumed. Smaller buffers mean less queuing delay, which actually improves latency for short flows. It's a rare case where the theoretically correct answer is also the practically better one. The old rule was built for a world of one flow. The new rule is built for the